Okay, last page. My favorite number, by the way. Oops, sorry, I scrolled too far up. My favorite number, though, is coming up. I can't focus on it. But before we get into this favorite number, let's talk about a very common application or a very common thing that happens when you have exponential functions. They model compound interest. And all compound interest is, it's the concept that if your bank gives you interest on the money you have in the bank, that interest, which then goes into that same bank account, helps generate a little more interest. And, that means the next time you get interest, you're going to get even a little more interest. So this is the concept of just as long as you keep the money in the bank, it's going to grow, but it's going to grow faster the more it gets. And the more it gets, the faster it grows. And it's a feedback loop. It can start off very small, but over decades or, even, several decades, you can have a lot. It can be a significant impact on how much money is in your bank account. But at any rate, this formula is just the basic formula to give you the amount of money in your account given a certain interest rate. The one extra variable here, this n, this relates to, well, we're human. We don't give interest continuously. Your money isn't literally generating you extra interest at every single second. They generally give you your interest maybe once a year, maybe once every quarter of the year, so quarterly. Maybe they do it monthly. Probably no one would do it every day. But basically, n is just the number of times throughout the year that they will give you your interest. They'll pay you that interest to the account. So you will do a little better if you get your interest, more frequently. The higher this n, the better off it'll be for you. But there is a limit to this too, as we'll kind of explore in this minute. But for now, let me just do this example and just use the formula. So if you deposit $9,000 into an account that pays 1.46 annual interest, find the balance, or the amount of money in your account, after 3 years. And this is when the interest is compounded quarterly. So this is just have to break down, this is just telling us which letters to plug in here. So 9,000 is the initial amount. This is called the principal, so that's the principal. The 1.46 is sort of the rate, just mind you, we will want to write that as a decimal, so R will be not 1.46, but 0.0146. We want to find the balance after 3 years. This time is in years, so that's RT. And the last part, which is tricky, is the interest is compounded quarterly. That means it's compounded 4 times a year. And that basically means that this is R. 4 is Rn. And so if we just plug all that in, we get the output. So I'm going to write 9,000, 1 plus 0.0146 over 4 raised to the power of 3. And I have forgotten, I was double checking this earlier to see if they got this. There's a typo on this note, which is very annoying. There should be an n right here. The time should be times n. Merp, that sucks. That's not there. But yeah, this is actually 3 times 4. But anyway, if you want an explanation of that, by the way, so if this represents the number of years, the idea when you compound interest 4 times a year, the actual number of times this compounding is going to happen is 3 times 4, so 12. They're actually going to give you interest 12 times over 3 years because each year they compound 12 times. Regardless, this is the number crunching. We'll just do 9,000, 1 plus 0.0146 over 4, and that's raised to the power of 3 times 4, and we get how much money you'd make in 3 years, or how much money I should say, not you'd make. You wouldn't make this much money. You would make 402 from your 9,000. It grows $402 just for sitting in your bank account at a very modest interest, 1.46. So that is our amount. I'll put that approximately that. Okay. Now, how does this relate to my favorite number? Well, let's talk about how we can arrive at this number, where this number comes from, and we'll get into a little bit more later. So the value E, which by the way is named after a guy named Euler. You could kind of, if you want to pretend he's called Euler, you can, but it's actually pronounced Euler, but anyway, it's his number because his name starts with an E. It is an irrational number. It's kind of like pi. It's a very specific decimal number. And if you raise it to the power of x, if you use it as the base of an exponential function, it has some very particularly unique properties, like truly powerful and unique. One, it shows up in nature a lot, but two, it can be used a lot, especially in things that model like computer systems. So you won't learn about that until much, much later, but for now, it's just worth knowing about good old Euler's number. But first, where does it come from? And there's a couple places you can derive it, but one of the most convenient ways for us to derive it is, what if we explore the idea of your bank giving you interest not every month, not every day, not every minute, not even every second, but in theory, if the bank was just continuously giving you the interest you were due. Now, to be clear, it's going to give you interest in very tiny quantities because you're only due a tiny percentage of the interest at any given moment. But if we explore what happens if the bank gives you interest continuously, or as close to continuously as possible, the amount of times they're compounding goes up and up and up and up, what's going to happen? What will your approximate interest rate kind of condense to? And I'm not going to go into too detailed explanation of, you can see the similarities in form, but I'll just say that this is going to kind of represent the base, they've taken out the n here. Also, they've taken out the time here, the power of t. But we're just going to explore, strictly speaking, what happens to the 1 plus 1 over x to the x. We're going to explore what the base would start to look like if we were having higher and higher amounts of compounding. So let's just use this formula with higher and higher numbers. We'll do 10 to the first, or 10. So that will look like 1 plus 1 over 10 to the 10. And just punch that into a calculator, see what we get. Ready? 1 plus 1 over 10, and we'll raise that to the power of 10, and we'll get 2.59. So I'll just write that down here, by the way, 2.59. Okay, so what I'm trying to explain here is, effectively, if you compounded 10 times a year, which is less than 12, by the way, so it's not even monthly, but it's more than quarterly, you kind of have an effective base. The effective base of your interest formula is like 2.59. So what happens if I just add an extra 0 to both the power and, critically you have to do it to this as well, to the denominator here. So now we're going to compound 100 times a year. And we get, it's not a huge difference in numbers. It's 2.7. Okay, so this is 1 plus 1 over 100 to the 100, and you get 2.7. All right, let's just keep doing that a few more times. So add another 0 here, another 0 here. Oh, it's even less of a change, 2.71. Okay, so 1 plus 1 over that, 1,000, and it's 2.71. Let's do it 2 more times if we can. So another 0, and you got the idea, so I won't write it for these last two, I'll just write the decimals. So this is going to be 2.7, oh, that's still 1.18 I'll put, and then one more time, 2.718. Okay, it is like, is it stagnating? The number's not really changing. What's happening is, this value, as you make this x bigger and bigger, is approaching a certain number. Want to guess what that number is? Told you that e is some random irrational number. This is approximately e. E is about 2.71877. So, by the way, I don't know if you have these calculators, but you can find e on a lot of calculators. Just like if you can find pi, you can hit shift pi, and then you can like have to hit S to D, but you can see the decimal for pi, 3.14159, blah, 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 blah. You can do the same with e. You can I hit the red button for e, and there's e, and it'll show you it's 2.178281828. That may look like it's repeating, by the way, but it's not. It is an irrational number. But yeah, that's my special number e. It's my favorite number. What would the graph of e look like, by the way? Well, all you really need to understand is that e is greater than 1. So it's going to be an exponential growth function. This, with a leading coefficient of 1, would cross through at 1, the kind of default, and just spike up just like any other function. Sorry, I left this out, but this graph is also meant to represent essentially the exact same shape because it's the graph of what this thing looks like, I believe. If I'm remembering what I do with the notes properly, it's just showing. No. Actually, you know what? I forgot that I was supposed to draw this graph to show what's happening to the to these numbers. If you plot these numbers with respect to x, actually, sorry, the shape looks something like this or something, where it approaches e. Asymptotically approaches e. Sorry, I messed that up. That's not a big deal. It's just trying to show that this approaches this number e, 2.7, 2.718. But anyway, the last thing to end off on is this, and this is a very theoretical concept, but what would continuously compound interest look like? Well, there's a continuously compound interest formula. Not that anyone would actually compound interest continuously, but if we did, it'd be modeled with e, as you can see, instead of the whole 1 plus 1 over Rn. A few things, for reasons that are more complicated to explain, cause the interest rate to be multiplied by the time, so that's a bit different. And if you're wondering what is the point of something which no one does, this is the model which effectively models a lot of things in real life which grow exponentially. So you use this less to model interest and more to model like bacteria and stuff. But for now, let's just do a quick interest problem, the same one as before, again, filling in with the numbers we got. So this is our principal, this is our rate, except for it's 0.0146 is our rate. Our balance is t. Sorry, not balance. Our years is 3, which is t, and this is compound continuously. So literally every single moment they're compounding. Oh my gosh, sorry.